about myself. I do a lot with ASHRAE. I spend time on technical committees. I'm leading technical committee 7.7, which is test and balance. Chair of that. I'm a member of 62.1 ventilation committee. And I previously was on 90.1 energy. So I've been involved with two of the major standards in ASHRAE. And we'll start. Okay, so most of us understand that conditioning outside air uses a lot of energy. Certainly up in the Northeast, where we have a heating dominant this time of year, it's even more expensive. I don't know. I'm an Eversource customer, and I received an email and a letter that basically said, "Hey, guess what? Your heating bill is going to be 27% more this year than last year." That's really pleasing. So we got to do what we can to save energy, and airflow measurement is certainly a key component of that, and we'll discuss why. In this EPA report that was done, they did a study of several buildings. In this particular report, 367 buildings, and the mean ventilation rate, you can see there was 105 CFM per person, so more than 5 times what the actual rate should be, because there wasn't many controls on these systems, and basically the air handling units were set up and forgotten about, and they just ran wild. So there's a lot of opportunity to save energy out there. But since my time on 90.1 and I switched to 62.1, I'm really focused on health, especially post-COVID. It's very important, and there's a lot of benefits to providing more ventilation than the minimum standard. You know, ASHRAE 62 and the IMC are the minimums, and we tend to design as the minimum as the maximum, or the speed limit. And then we're really pushing the limit there if we treat the minimum as the maximum, especially when it comes to time when we want to provide more outside for something like a pandemic. So this study that was done by Lawrence Berkeley Labs shows an increase in productivity and value to the employer for the people working in the buildings. I mean, the reason why we build buildings is so people have a place to be sheltered, that people can perform and create value. This has a direct correlation between sick building syndromes and increase in ventilation, or the decrease in ventilation. So a 15% increase in symptoms as the ventilation rate went down, and a 33% as the ventilation rate went up. Anyone that's running a business has to understand that health costs, the health insurance continues to go up at a great rate, and it's one of the highest burdens on an employee's salary. And we don't want the employee to have to use his health insurance. We want to make sure everybody's healthy, and there's a benefit to that by providing more ventilation. This study, which was done by MIT, said 57% of all sick leave was due to poor ventilation, and the benefits can be anywhere between $6,500 to $7,500 per year in productivity. And guess what? It improves the value of the space. A healthier building can get more rent, or can sell at a higher rate. Throughout this presentation, I will have these 3D barcodes. You can click on them as I'm doing the presentation, and I'm willing to share the PDF of the slides. They will also have hyperlinks after the presentation. So what are we doing when we're ventilating? We are, diluting the air. We are replacing the air indoors with air outdoors, and we're trying to remove the mass, an aggregate of matter in the space. And we're also trying to remove it through high-level filtration or targeted filtration. Interesting thing is ASHRAE 62, the minimum requirement for filtration is a MERV 8, and the IMC doesn't have a minimum requirement. So this is really something. The ICC actually had a change that was requested for the 2024 version for a MERV 13 as a limit, but they decided not to incorporate that change. I wish they had, because it really improves the health of people. Well, most of you know that mass flow rate is the mass over time, and so when we're talking about diluting the air, we're talking about moving mass. We're talking about the weight of the air, not necessarily the volume of air. So we're talking about air in standard cubic. Those of you who understand there's a density impact when you're talking about the air. So there's a relationship between the mass and the volume and the density. So I found this little image, and I thought this kind of shows it really well. The volume in the two jars are the same, but the number of marbles on the left is much more than the ones on the right. So it has a higher mass, and the density is different. So this is important because when we're talking about airflow, we're related to the air is going to change with temperature and pressure. And ASHRAE standards, as well as the IMC, they're written in volumetric airflow or actual airflow in CFM, but they are standardized. They're standardized at sea level at 70 degrees. So at 0.075 pounds, that's our mass weight of air per cubic feet. So if you are not running in standard cubic feet a minute, you have to make some adjustments for this. And I was involved in working on an addendum that came through, and I'm going to show you kind of the background to the addendum. So anybody that's gone up and skiing in the high mountains in Denver and Colorado know that the air is a little bit thinner up there. As you increase in elevation, your density changes. Same thing happens in temperature. In the summertime, our air is thinner. In the wintertime, it's heavier. And the moisture has a very little bit of effect. And typically, the moisture sensors, RH sensors that we have today, aren't accurate enough to really pick up the difference. But if we replace the density with an airflow value, you can actually see what the differences are. So the green represents what the standard conditions are, and everything beyond that, above or below, is a divergence from that. So as an example, if we take Colorado Springs in the summertime, using the design cooling temperature, then you can actually be 24% under ventilation just by using volumetric airflow, right, without correcting for the airflow. So we put in the fourth an addendum H, which was published this spring, that engineers have to correct for this density impact. And it's very good. So there's also an advantage in the wintertime, or, in Edmonton, the design temperature is -30. You can see you can be 15% above minimum ventilation. So you actually, if you use an EBTRON and you run the standard airflow conditions, then you can actually modulate automatically as the air gets more dense in the wintertime, and then you can save energy. Or you can do that calculation yourself using the airflow measurement and another temperature sensor. So this is something that I show quite often now because a lot of people aren't aware of it. I'm a big person that's into history. I think we can learn from our history. It's important to recognize what's happened in the past so that we don't repeat the same mistakes in the future. But interesting enough, Massachusetts was the first state in the nation to actually have a law for ventilation. And this happened way back in the 1800s. And that started with having a law for public spaces and auditoriums and for schools. And the ventilation rate for schools back then was 30 CFM per person. And for other public spaces, it was down to 20 CFM. But you can see over time, the ventilation rate has dropped until it hit rock bottom in 1981 because we had the oil crisis in the 1970s. And this caused everybody to get tight, even in make tighter buildings. Even ASHRAE said, well, we got to try to save energy and reduce the ventilation. Well, what happened was we created sick building syndrome. During the 80s and 90s and into the 2000s, people were getting sick going to work or living in buildings where they had general systems. And so in 1989, the ventilation rates were shot right way up again. But since 2004 and addendum in 2001, the ventilation rates, when they were switched from just a CFM per person to a CFM per person and a CFM per square foot, they have been reduced. And some of our highest density spaces like auditoriums and conference rooms are the most, I would say, unsafe because they have the least amount of ventilation. They're down to rates about 6 CFM per person, which is not a lot, just barely above the 1981 rates of 5 CFM per person. So One of the things that I look at, well, the title of ASHRAE 62.1 is ventilation and acceptable indoor air quality. It used to be ventilation for acceptable indoor air quality, but this is a recent change, basically recognizing the fact that you can have other technologies such as UVC or filtration that can help with the air quality. Well, if we look at the definition of what 62.1 is to provide the minimum. As I said, we don't have to design right at the minimum. We can always design a little bit greater than minimum and operate between two different points. At least gives us some leeway in case we need an increase, and the systems can already handle it. Well, what is the definition of acceptable within 62.1? And that's when no known contaminants are in the air. But if we're designing a building, how do we know before we build the building whether there's any contaminants in the air or not? The other interesting thing is the standard is based out of a substantial majority of 80%. And this ties back to some research that was done in the 1980s around body odor and what was acceptable to people that were in the space and new people walking into the space. So, it's really something you have to consider. There's a lot of things that are happening in the space right now. There's a lot of VOCs that are being generated that we're hardly aware of, and more studies. I'm reading studies almost weekly about what's happening, and it's something that we should be concerned about. ASHRAE Standard 62 has the indoor air quality procedure, and a recent addendum put forth these limits. But these are actually hazard limits. These are limits that, at the point where if you reach these, it's really bad for the person. So if someone says, hey, I can put in an air cleaning system and I can save you energy, and the formaldehyde is going to be at 30 micrograms per cubic meter, so you're going to be all set. Well, you're only 3 micrograms below the limit. So I would really consider that. You should be much lower than that with respect to that. Since COVID, since the wildfire smokes, there's been a lot of action happening around the country as far as Senate and House and congressmen pushing forth bills. And this is just a look at what's happening in Massachusetts right now. And there's a lot going on to try to improve the filtration, to try to improve the monitoring. Boston has one of the oldest school systems in the nation. Most of the schools aren't mechanically ventilated. There are other cities that are similar around the country. So, and a government accountability office did a report that basically said 50% of our schools are failing mechanically, and they really need an update. So that's why there's a big focus on schools, but just in general. And this last one where I have this 3D barcode there, or QR code for the Model Clean Air Act. The Model Clean Air Act was something that Johns Hopkins Center for Health Security had put forth last year. And their goal was to make state laws again to protect indoor air quality, because there's nothing that regulates indoor air quality. We have a building code, and that's it. Back in 1920, after Massachusetts started the trend, we had 20 states that had building codes, and that actually had laws for ventilation, and now we have 0. So I think post-COVID, with everything else that's going with wildfire smokes, we should really consider having a model law and give some power to the people that are living in buildings to actually complain or be concerned about where they're working or sleeping or going to school. So when we talk about ventilation, and we talk about, it's been well known that if you take a fixed damper position, so you have a balancer that goes in and sets up the damper at the full flow. Well, once you turn down that fan and reduce the flow, there's a linear change that happens across that damper. There's actually a pressure drop in the mixing box, and it causes a direct change linear to the supply of airflow speed. So basically what happens is if you drop the fan speed without changing that damper position, you're going to also drop the ventilation. Similarly, the same thing happens in DOAS. A lot of people consider DOAS, I'm just providing the ventilation air to the space. It's not conditioning the space. I'm not doing any VAV with it. So why do I have to worry about, doing any measurements? But once you do any sort of zone control, VCV, CO2, people counters, or occupancy sensors, and you modulate to try to reduce the airflow to the zones, you can completely change the balance of the entire system and the pressures in the systems. And you have to add a VFD, and now you have to add dampers and airflow measuring devices at the zone level, as well as the outside air, in order to maintain it. Otherwise, you're not going to maintain it. Some zones are going to be overventilated, some zones are going to be extremely underventilated. And this is represented in the ASHRAE DOIS design guide as well. So one of the things that when I was involved in ASHRAE 90.1, we put forth an addendum that basically made multiple speed on all constant volume systems, whether it be water-cooled or direct expansion type of systems. Basically, everything above 4 tons has a VFD on it today if you buy a new piece of equipment. So they're changing the fan speed with the load in these cases. So if you're using even a simple 2-stage thermostat, on second stage is at full speed, on first stage, then it's on a low speed. And you're going to have the same problem if you're not measuring airflow. And I tell you, a lot of people are not measuring airflows on small rooftop units or even small hydronic systems. Now, there's a reason why the GSA has a minimum requirement, a baseline requirement for airflow measurement on VAV systems. It's because of these changes. Their Tier 2 requirement requires airflow measurement on all systems. I argue that we should have airflow measurement on all systems because all systems are now dynamic. There's basically nothing as a constant volume system unless it's a residential. Even residential systems tend to be variable speed these days. International Green Building Code, which is based on 189.1, also has a monitoring requirement for ventilation on airflow measuring on all systems, especially with respect to DCV. They do have an exception here for constant volume systems that don't use DCV as long as you're looking at the intake damper. But we're going to discuss that in just a minute and why that exception shouldn't exist either. But it's not just what's happening with the speed of the fan, it's also what can happen outside the building. The wind blows almost every single day, occasionally, especially in the Northeast here. We have some very windy days. They call Chicago the windy city, but Boston is definitely much more windy than Chicago on a regular basis. And the wind, when it blows, it never blows in the one direction. It's always changing direction, and it's always changing speeds, and it has gusts associated with it. In fact, this is a graph on the left, basically is from my home weather station, and it's only taken over a few hours from noon to 6 p.m. and the wind direction changed 90 degrees in that time frame. So looking at ASHRAE fundamentals, I can show that a crosswind across a damper generates a negative pressure on that outside air intake. And in this example, a 25-mile-an-hour crosswind is almost 0.2 of an inch negative pressure. Well, this is going to be the same thing as having restriction in the return. It's going to suck against that mixing box, or going to suck against the fan curve. So in a DOIS system where you may not have a mixing box, it's just you're just taking an outside air, it's going to work against the fan curve. So where you set it up for 10,000 CFM and you didn't make any adjustment, and you have this wind blowing across that outside air intake, all of a sudden you add this 0.18 inches to the fan curve, and you're really providing 9,100 CFM of outdoor air. These are things that people don't think about. This is things that people at EBTRON think about all the time, because this is all we do. We focus on measuring airflow. And this is a measurement that we actually did at EBTRON, which is plotting the airflow with the damper at a fixed position and just watching the air change in the mixing box and at the airflow measuring station. As you can see, the mean of this was about 85% of what you expected. So the wind can change it. It can provide more air than you want. It can provide a lot less air than you want. And it depends on the wind speed. Another thing that happens is stack effect. Stack effect can certainly change the impact of the rooftop unit. And in this example, I'm showing that stack effect isn't only in the super tall buildings. It can also happen in a 4 or 5 story building. Basically, if you have a rooftop units and you have the ductwork going all the way down, you basically build a chimney. And if anybody has a fireplace at home and they don't have a cover in their fireplace, this time of year you are sucking the heat out of your house quite quickly. Well, it's the same thing you have happening with a air handling unit on the roof and a duct going all the way down. You can take the air out and it works pressure against the mixing box and can reduce the amount of outside air, even though the air is more dense. And the same thing happens in the summertime. You can cause the air to come in much quicker when it's hot and humid. Hysteresis. A lot of people aren't that familiar with hysteresis. Well, hysteresis is the potential for something to not land in the same spot, depending upon the direction you're moving. In my past, I worked for Belimo for 18 years, and I was very much involved with the actuators. And I can tell you that the actuators aren't perfect as well. So one of the things that happens is, we have these dampers with these tight seals. Well, why do we have tight seals? Because 90.1 says you must have a class 1A damper. So this is another thing I was involved with when I was in 9.1, was putting these tight seals on the damper. Well, these tight seals actually cause the damper to really stick in place, and the actuator actually has to pop the damper open when it's going from full close to an open position, min position. But when you go from an economizer position back to the min position, there's no popping, there's no resistance except for the edge seals, and they're not as bad as the blade seals. And that's why on the graph on the left, it basically shows you're ending up in two different positions. You also have linkages that can have slops. Even if you have a direct drive actuator, like in this example, you still have linkages on the dampers. And these things wear over time, as well as the seals that will over time, and dampers can break. So over time, things just continue to get worse. The solution is to measure the airflow. And then you can always position directly for the airflow instead of where the actuator position is. And actuator position feedback just tells you where the actuator is. It's just feedback of the motor inside the actuator, not the actual damper. And the motor itself actually has hysteresis. The actuator manufacturers built in mechanical hysteresis and electrical hysteresis so that they don't burn up the motor. So you have all this stack up of hysteresis. It's really hard to hit the right spot. That's why the graph on the left looks the way it does. You can't rely on damper positions, as well as the fact that dampers are not linear devices, and they have damper effects as well. So everything I just talked about, this is a quick graph to say, hey, there's many things that can impact the outside air delivery. If you're not measuring the airflow, then you have no idea where you are. You can't set it and forget it one time. Unless you have a balancer going out there every single year, then you're not going to be able to maintain what was originally set up. Airflow measurement, especially outside for a balancer, is the most difficult thing they have to do in the job. And it's very tough to set up to begin with and keep it going. So when you have an airflow measuring station, it's more than just ventilation. You can also control the pressurization, because the pressurization is the mass flow of air going in and out of a space or in and out of the building. And we refer to this as the pressurization flow. Depending upon how leaky your building, it depends upon what your differential needs to be. The greater that you have air going into a space or the building, compared to how much exhausting, the greater your pressure differential. When you start getting in demand control ventilation systems, you start reducing the amount of intake, and you're not tracking the intake flow with the exhaust flow, then you're going to be reducing your pressurization. You may actually go to negative pressurization. So the only way to ensure that you're maintaining a positive pressurization is to track the airflows. You got to track the supply, return, and the exhaust going out of the building. If you're not, you may have infiltration, and infiltration is going to bring in dirt. It's going to bring in moisture and heat or cold air through the walls, through the doors. And this is air that's not clean. It's not been filtered. It's not conditioned. And it's going to lead to uncomfortable spaces. In some cases, it can lead to mold on the walls and windows or within the walls, which generates spores. And living up in New England here, I recognize I've never seen dew points like I have the last couple of summer, where in July we're over a 70-degree dew point. It has gotten more humid. We do have a climate change effect, and these colors are different. If I showed you this dew point graph from 5 years earlier, that pink that's been encroaching in Rhode Island, Connecticut, and Cape Cod wasn't there. And so it's very important that we're controlling the airflow, especially on the East Coast here, because this humidity is one of the greatest loads that we have in our HVAC system. And if it's not going through the coil, then it's not being conditioned well, especially when you're looking at DOS type of system where you're doing most of your latent removal at the air handling unit itself. And of course, we've all experienced the wildfires. We don't have to have a fire next to us to get the smoke these days. It travels quite far, and the smoke is made up of VOCs and particulate. The particulate is the worst. That's what we see in the air quality index that's going up the greatest. Now, the tendency is to reduce the outside air when you have wildfire smoke. You don't want to do that. You want to make sure you're providing outside air to ventilate the contaminants inside and to maintain the pressurization. If you start reducing your outside air, then you may be infiltrating through the doors this smoke and getting into the building and not filtrating out. The goal is to filter out this contaminants. And guideline 44 will be coming out very soon from ASHRAE. And guideline 44 talks that you have to have a minimum of a MERV 11 filter to remove those contaminants. So it's this is something that you can do on a temporary basis. You can switch out filters, but if don't design your system with these things in mind, with COVID and standard 241, the minimum filtration requirement was MERV 13. So we should think about designing our systems to handle these extra these higher grade filters, or maybe having them as a minimum, because MERV 11 and MERV 13 actually improve health on a regular basis, not just during wildfire smoke or during pandemics. And as I said, you have all these things that can affect the ventilation, but also affect the pressurization of the space that are happening outside the building. So we have to be aware of it. If you're not measuring, you can't control it. So one of the things that we recently did, in fact, it was published on October 31st, Halloween of last year, 2023. And this was a new approach to DCV, because a lot of people were incorporating DCV incorrectly. They were using old values like 1,000 parts per million applying to all spaces, and that's not the right way to do it. And so basically what we tried to do in ASHRAE is we tried to simplify it, even though the simple method is not the most accurate method. There is a document that's been published to actually how to calculate it. There was an addendum that came out initially, which there's a more complicated method, but there was a lot of concerns that all the calculations would be a lot of burden for the engineering community. So instead, we made an assumption of what the makeup of the space is, because CO2 generation is based on the occupants. It's based on whether they're male or female, what their diet is, what their age is, what their activity level is. So we had to make these assumptions with doing this. But I want to show you some examples in this table. So we have these default CO2 limits. And let's look at a conference meeting room. Because the ventilation rates are really low in a conference meeting room, the steady state value is 2,500 parts per million. Not 1,000, 2,500 parts per million. Everybody was freaking out during COVID-19. Hey, we should maintain 800 parts per million. This is 3 times greater than 800 parts per million. And the same thing with an auditorium space. Again, a lowly ventilated spaces. These are the spaces we have to be most concerned about when we're talking about the cold and flu season, because they can spread the flu quite easily in these spaces. So in this addendum, we also have occupancy density adjustment requirements. If you aren't using the default occupancy density that's in ASHRAE 62 or the IMC, then you should be making an adjustment for it. Sensor placement, we have requirements for sensor placement, and the control requirements. This is the most important things. A lot of people would not activate the damper until it reached that limit value. That means you're underventilating the space the majority of the times. As soon as you go above the ambient, and the ambient can be anywhere between 380 to 420 these days. Once you start to go above the ambient in the indoor space, then you should be marshalling the damper open. And the good thing is you can use an airflow measuring station to limit it. You can limit it on the low end to prevent underventilation and control your pressurization, and you can limit it on the high end to provide not more ventilation than you really want to save energy. So just looking at this as a curve, you can see, this curve is basically specific. As I said, it's based on a metabolic rate, it's based on age. And a metabolic rate of 1.3 is basically what we're doing now. We're sitting watching me talk, basic office work. However, if you are more active, you're going to have a shift in this. But if you design a building, like a conference space, for example, and you design it for 6.2 CFM, and this is the steady state value, and then you want to control it at 1,000, you're going to be going from 6.2 CFM to 17 CFM, because that's what 1,000 parts per million means. There's a direct relationship between the CO2 value and the ventilation rate. So you can't control to a different number than what you're designed to. Otherwise, you're not going to be able to condition the air. You're going to be using up more energy than you expect. And just to show you what the metabolic rate is, this is a person walking around at 3.0. Or I have another chart here that basically says if you try to maintain 1,000 parts per million from just an office work at 17 to an exercise space. So if you took an office and you moved a gym in there and you didn't change the ventilation rate, well, and you try to maintain it at 1,000 parts per million, you'd be trying to drive 66 CFM per person into that space, trying to maintain that 1,000 parts per million. Your system is not going to work when you do that. So 241 is, as I said, came out in June of 2023. I don't know how many people are familiar with it, but it is very much a rate-based standard. So I'm just going to touch upon what this means. So we have the ventilation rate equivalent to clean air ventilation rate to the space, to the breathing zone. Okay, it's airflow rate per person, which is great because we can measure airflow rates per person with an EBTRON. The same thing with filtration. You want to know how much particulate remove or aerosol remove your filter is doing. And another way to determine that is the airflow rate. And so the idea is they have tables in there that tell you what the airflow rate of a MERV 11 versus a MERV 13 versus a MERV 16, and components that are not mechanical filters that clean the air in other ways. They're supposed to be independently tested to determine what this airflow rate equivalent is. So once you know what this airflow rate equivalent is, then you should be measuring it. You shouldn't put a filter in a system and call it equivalent clean air if you're not directly measuring it all the time, because things can get dirty. The prime mover that's moving the air through the system may not be moving the air as expected, and you don't know that if you're not measuring the airflow rates. One great thing about Standard 241, it has a building readiness plan that's supposed to be developed so you understand how the system is supposed to be operated during normal mode and how it's supposed to be operated during infection risk management mode, or IRMM. Okay, and it's basically the determination to switch it from this normal mode to the IRMM can be made by the building owner and the facilities operator. It can be made by the Department of Health. It can be made by the town or the city. It just depends. That's what the flexibility of the standard is. But at least it gives you the opportunity to do that. And one of the important things is this plan includes you have to understand what are all your dynamic changes happening in the building. You have to understand that you're measuring outside supply and return airflows. It's a requirement to do that. You have to understand what controls that can change the fan speed. You have to understand what the pressurization requirement is. You want to make sure that you aren't moving from a dirty space to a clean space. Just the same thing in a healthcare space. You don't want to move the air from a public space into an operating room. You want to go from the operating room and out. You want to make sure that the patient is clean. You want to make sure that there's an anteroom in between, things like that. So that's basically what the basis of 241 is based on. And there's functional test requirements. There's a lot of commissioning and functional testing that has to be done in both modes of operation, both normal mode and pandemic mode. And it's based off these ASHRAE standards. So EBTRON will definitely help you out in standard 241 as well as normal operation. And the great thing is once you're measuring the airflow, you can see what the airflow is for 62.1 or the IMC, what your ventilation rate per person, and then you can crank it up to 241 mode or IRMM mode. And just how much you cranking it up? Well, here's an example of the table. I put this together. This is basically showing what the 62.1 rates are and what the equivalent clean air rate of 241 is. And if you look at the office, It's not that big of a change, but it is almost double still. So you have to have 1.8 more clean air than you had before, a factor of 1.8. But a lecture hall, it's 6.3. A convention center is 9.7. What does this tell you? This tells you these rates are very low ventilated to begin with, and they're high density rates, and they want to have more of that. Obviously, you can't have 6 times more ventilation, so you have to have enhanced filtration. There's nothing better than filtration in the space with room air cleaners. That's the best source, collecting the contaminant at the source. Definitely, you should be increasing the ventilation, and you should be adding other sources to control the infection, whether it be UVC or other air cleaning sources as well. But if you're not measuring it, you have no idea what you're providing to the space. So whether it be ventilation air or clean air through the filtration device, again, it requires airflow measurement and validation. And here's an example. This is this little graph is taken right out of the 241 calculator. And this is showing you what the equivalent clean air from each type of filter is in this standard. I think this is really cool how this standard is doing this. In fact, we're looking at this in a standard 62.1 because there is a concern about energy. We want to make sure that we are addressing the energy concern, but we also want to make sure we're addressing the health concern. Understand what we're trying to remove, what we're trying to achieve in the buildings. And PM10 and PM2.5 are some of the most critical things these days to people's health because they get deep in the lungs, just like aerosols from viruses get into your lungs. And this is just a drawing that basically shows how the air cleaners can be independent of the HVAC system as far as the conditioning system or the DOS system. They may be a separate loop or they may be in an air loop. And each of these VAC loops, again, should be monitoring. Otherwise, you can't determine what the performance of that air cleaner is as far as the rates are concerned. And here's that standard, that independent test, and I meant in normative appendix A. Any system that you considered installing in a building should be tested independently. You should see a third-party test associated with that. And this is just a statement again saying, hey, the air cleaning installed in the system should be rated for the same conditions that it's installed at. And you have to measure it in order to verify that it's the same conditions that it's installed at. Lastly, I just want to say, hey, EBTRON is doing our best to continue to lead the industry in our technology. We continue to improve with our products to try to give you the best solution on the marketplace. I'm proud to say that we recently got 2 patents in the United States. We have 2 patents in Canada. We're going about getting a Mexican patent and a European patent. I've just been notified of those things. And so what are these patents are about? Basically, a few years ago, we decided to include a humidity sensor into our airflow probes as an option. And we're in a great climate here where a humidity sensor makes sense. Basically, so we have an ability to basically have an airflow meter, a BTU meter in the airflow. So we are not only measuring airflow velocity, where you can calculate the CFM, knowing the size of the ducts that it's going through, but we have the best temperature sensor in the marketplace. Our beading glass temperature sensors are the most accurate airflow measuring device that you can buy as far as temperature. You can compare this 0.15 degrees accuracy to anybody else out there that's providing a temperature sensor, and you'll see that we're probably twice, if not 3 times more accurate. And we don't just have one 6-inch probe going in the duct that's measuring the average. Every time you have a node, you get a different temperature value. Well, we combine this with a humidity sensor and a onboard barometric pressure sensor. Basically, you now have a psychrometric chart inside your HVAC system. So if you have one of these EBTRONs with the humidity sensor and our pressure sensor installed in a supply, outside, and a return, you can do full psychrometric calculations. You have an energy meter installed in your airside, and you can see what's happening. So if you're really concerned about energy, this is one way to track things. You can also use it for fault detection and diagnostics. In addition, this pressure sensor can be enabled to automatically adjust if you're running in volumetric airflow and not standard airflow, to automatically adjust for that altitude change that I talked about. So it can change the volumetric air fluid density automatically, or it can change even with the weather. You know, if it's a rainy day, the pressure is the air is less dense than a different day. So you have to watch what's going on. We're also proud to announce that we released this new product this year called the XDX 1000. And this is a smart display that we can tie up to 16 EBTRON transmitters and other devices in the future too. And this is going to allow you at one point to monitor up to 16 devices. And you'll be able to configure and set up and copy configurations from one transmitter to another transmitter. You'll be able to track what's going on from one single location. Right now, we're running this on our own Ethernet bus. Basically, it's BACnet, but it's our own BACnet bus. It's not tied in the building automation at this time, but the goal is to tie it in the future. But this allows a operator to see multiple airflow stations from one point and allow a balancer to go in there and configure the system from one place, or a control contractor can configure from one place and actually measure and balance the building from one different place. And it gives you one point of reference to see things going on. And you can see in the screen on the right, you know, with our technology, we don't just measure relative humidity, we can measure dew point as well. And if we're measuring dew point, then hey, you can use it on a DOA system and maintain nice dry air to the space. Or if you're looking at enthalpy, you can use it outside air and use it for economizing. I'm happy to say with EBTRON, we got you covered, and